So today we're going to talk about another concept from physics that we can calculate using our slicing technique. It is called work. So some preliminary facts. Work is force times distance, and force is typically measured as weight. So this is actually, we're going to think of this as weight times distance. And weight is mass times the acceleration of gravity. And we've got a handy little chart with some units and just a reminder about some stuff from our last lesson, that in one dimension you can calculate mass by doing density times length, 2 dimensions, density times area, and in 3 dimensions, density times volume. So let's calculate how much work is done by lifting 2 kilograms of iron 3 meters off the floor. So this is not a calculus problem, this is a physics problem. And we're just going to use our formula, work equals weight times distance. Okay, so work equals weight times distance. And weight is mass times the acceleration of gravity. So weight is mass times the acceleration of gravity, and then times distance. Okay, so the mass of this piece of iron is 2 kilograms. The acceleration due to gravity is 9.8 meters per second squared, and we are moving this thing 3 meters off the ground. So this comes out to 58.8 joules. Joules is the units for work when you're working in metric system. Okay. Let's complicate it a little bit. A 45-meter rope with a mass of 30 kilograms is dangling over the edge of a cliff. Ignoring friction, how much work is needed to pull the rope up to the top of the cliff? So what is wrong with the following solution? Work is force times distance. Force is just another word for weight, which you calculate by doing mass times the acceleration of gravity, and then distance, 45 meters, to pull the rope up. So the problem is that, let's draw a picture of this. Here's my cliff. Here's my rope hanging 45 meters down the edge of the cliff. The problem is that this piece of rope doesn't have to move 45 meters. It barely has to move at all. And this piece of the rope has to move 45 meters. But this spot on the rope might have to only move 10 meters. So not every single piece of the rope has to move 45 meters. So we need to break the rope up into little slices. Each one has to move approximately the same distance. So let's pick a random slice of the rope to pull up over to the top of the cliff. So I'm going to have this little teeny tiny slice of the rope. So tiny, we're going to say that it has to move a distance of h meters. And it's so tiny, its length is just delta h, some teeny, teeny, tiny slice. Curly bracket. Okay. So let's just draw a picture of my slice. It's a little teeny tiny slice of rope. Its length is delta h. And I need to figure out how much work we need to do to move this slice. So work on my single slice. Well, work is weight times distance. Okay. The weight of this little slice is mass times acceleration of gravity. So I need to know the mass of that little slice, then multiply times the acceleration due to gravity, then multiply times the distance. Well, what's the mass of this little slice? Well, mass of the slice is density times length. Density times length times the acceleration due to gravity times distance. And the density of that little slice, so the density of the entire rope is, remember, density is the amount of stuff that you can fit inside something, right? So density for this rope is going to be measured in kilograms per meter, the mass per meter. So I know the mass of the entire rope is 30 kilograms, and that's going to be split up over 45 meters. So the density of my rope is 30/45 kilograms per meter. The length of my little tiny slice is delta H. The acceleration due to gravity, because I'm dealing all in metric units, kilograms, meters, is 9.8 meters per second squared. And then the distance that that slice needs to move is H meters. So that is the work done on that one slice. And then I need to add up all of those slices. So the work on all slices is just a sum of n slices, and each one has this amount of work to be done on it. So 30/45 times 9.8 times H delta H. And I'm adding up n of those slices. Finally, I take a limit as n goes to infinity to get the exact amount of work done. Limit as n goes to infinity of this whole sum, and that is going to translate to an integral. 30/45 times 9.8 times h dh. And then the bounds of integration have to do with how much does h change. So I'm going to go back to my original picture to determine the bounds of integration. What is the smallest this value of h can be? The smallest distance that a piece of this rope needs to be moved is 0. And the largest distance that h can be, the largest distance a slice of rope needs to be moved, is 45 meters. That's the height of the cliff. So I'm going to integrate from 0 to 45. And this is a pretty straightforward integral to do by hand. And I'm just going to tell you that it comes out to 6,615 joules. Again, that is the metric unit for work. All right, next we have a water tank in the shape of a right circular cone, height 1 meter, top radius of a ½ meter, and it has a column of water that has a height of a ½ meter inside of it. So we want to find the work that must be done to empty the tank by pumping the water over the top edge. And they've told us the density of water is 1,000 kilograms per cubic meter. So I need to take the water in there and slice it up into slabs so that each slab has to move approximately the same distance to get out of the cone. So I'm going to pick a random spot along here, somewhere in the water, and I'm going to draw a slab. So some like slice of the water. It's going to look like a cylinder with some small amount of thickness. So I might draw a picture of the slice. It's circular, and it's got some like little bit of thickness here. So let's say this small slice of water, it needs to travel up and out of the cone. And let's call that distance that it needs to travel h, which means the distance from the slice to the bottom of the cone would be 1 minus h. And then the thickness of this slice is delta h. So my thickness is delta h, and I need to know the radius of that slice in order to calculate anything about it. Its volume, its weight, its mass. I need to know its radius. So that distance we'll call r. And I'm going to use similar triangles to calculate r in terms of h. Okay, so I've got this right triangle. This is a distance of 1. This is a distance of 0.5. And then I have my slice located partway up the triangle. This is a distance of h, which means this is 1 minus h. So similar triangles, I have this large triangle, and then I have this smaller triangle that is similar to it. So I'm going to use a proportion, big to small, big to small. And that distance is r. That's what I'm looking for. So I have 0.5 is to r. That's big triangle to little triangle. And then the height of my big triangle is 1. And the height of my little triangle is 1 minus h. And then I just need to solve this proportion for r in terms of h. So I cross multiply, I get r is 0.5 times 1 minus h, or 0.5 minus 0.5 h. So the volume of this slice is pi r squared delta h. It's just a cylinder whose height is delta h. Okay, I'm going to replace the r with this expression. So this is pi times r, which is 0.5 minus 0.5 h squared delta h. So I know the volume of the slice, which means I can calculate the mass of the slice because they told me the density of water. So the mass of my slice is density times volume. And density is 1,000 kilograms per cubic meter. And then the volume up here is in cubic meters, which is pi times 0.5 minus 0.5 h squared delta h cubic meters, which means the cubic meters cancel, and this is just kilograms. All right, so once I have the mass, I can calculate the weight of my slice, which is mass times acceleration, acceleration due to gravity. So the mass is the previous expression I just wrote down here, and I'm going to simplify it a little bit. So I'm going to have 1,000 times pi, 1,000 pi times 0.5 minus 0.5 h squared delta h. And then I have to multiply times the acceleration due to gravity, which is 9.8. And finally, that's the weight. So I can now finally calculate work on that slice. The work done on that slice is the weight of the slice times the distance that we have to move that slice. Okay, so the weight of the slice is the previous expression. So this is 9,800 pi times 0.5 minus 0.5 h squared delta h. And then the distance we have to move that slice, let's go back up to my picture, figure out how far we have to move each slice. So this is my slice of water right here. I have to move each slice of water h meters. So that's the work done on a single slice. My work done on all the slices is just a sum of n slices that look just like this one. So it's going to be 9,800 pi times 0.5 minus 0.5 h squared h delta h. And then finally, the total work, take the limit as n goes to infinity of the sum. And that is going to translate to an integral. We've got 9800 pi times 0.5 minus 0.5 h squared times h dh. And then I just have to figure out the bounds of integration, which always helps to go back up and look to your picture. So h is the thing that's changing here. So I have to figure out what is the smallest h can be and what is the biggest h can be. So what is the smallest distance of any slab, the smallest distance that it would need to move to get pumped out of here? So this top slab would need to move precisely half a meter to get pumped out. So the smallest distance h, the smallest value h can take on is a half. That's the smallest distance any slab needs to go. Now this slab at the very, very bottom here, this teeny tiny little slice, it needs to move 1 meter to get out of the tank. So that is the largest h value. So those are my bounds of integration, 0.5 to 1. All right, this is a fairly straightforward integral to evaluate by hand, or you could use a calculator. I'm just going to skip the evaluation part here. The difficult part is setting up the integral. So we'll just say it's this many joules.